Hello friends, today let us study RLC series circuits and series resonance. What is a RLC series circuit? When a resistor, inductor and capacitor are connected in series across a common voltage supply, the circuit obtained is called a RLC series circuit. It has three basic passive components which are a resistor, inductor and capacitor, and all these three components have very different phase relationships to each other when connected to a sinusoidal AC supply. So let us study the different phase relationships. In a pure ohmic resistor, the voltage waveforms are in phase with the current, as we can see here. In a pure inductance, the voltage waveform leads the current by 90 degree. We can remember this by the mnemonic ALE, where E stands for EMF, L stands for inductor, and I stands for current. So EMF leads the current by 90 degree in an inductor. In a pure capacitance, the voltage waveform lags the current by 90 degree, but we can also say that the current leads the voltage by 90 degree. We can remember this by the mnemonic I's, where I stands for current, C stands for capacitor, and E stands for EMF. So current leads the voltage or EMF in a capacitor. We can also remember this by a one-word mnemonic civil, where CIV implies in capacitor the current leads the voltage, and VIL implies in inductor the voltage leads the current. This is a summary of what we just studied. In a resistor, the impedance is equal to R and there is no phase difference. It has no reactance. In an inductor, the reactance is equal to omega L and it has a phase difference of plus 90 degrees since voltage leads the current. And in capacitor, it has a reactance of minus 1 by omega C and it has an angle difference and the negative sign is because of the minus 90 phase difference since current leads the voltage. Now let us study the analysis of a series RLC circuit. For the analysis of a series RLC circuit, we need to take into account both the magnitudes of XL and XC to find the overall circuit reactance. In series RLC circuits, there are two energy storage components, as we know that inductance and capacitance are both storage elements, and hence RLC series circuits are classified as second order circuits. Now in a series RLC circuit, the instantaneous current flowing through the loop is the same for each circuit element R, L and C, and the individual voltage drops across each circuit element of RLC will be out of phase with each other. For the resistor, it would be in phase with the current. For the inductor, the voltage VL would lead the current by 90 degree, and for the capacitor, the voltage VC would lag the current by 90 degree, as we can see here. Since the current is common to all three elements in the series RLC circuit, the vector diagrams will have the current vector as the reference with the three voltage vectors for VR, VL and VC being plotted with respect to this reference of a current. Therefore, we'll have to find the supply voltage Vs as the phasor sum of the three component voltages combined together vectorially. Now, applying KVL to the circuit, we get Vs minus Vr minus Vl minus Vc equal to 0. Now, substituting the values of Vr, Vl and Vc as IR, L di by dt and Q by C, we get Vs is equal to IR plus L di by dt plus Q by C. Now, Vr is equal to IR sine omega t plus 0, since I is equal to Im sine omega t, and VL is equal to IXL sine omega t plus 90 degrees since it leads the current by 90 degree, and VC is equal to IXC sine omega t minus 90 degrees since it lags the current by 90 degree. Now this has been shown in this phasor diagram relationship. Here VL leads the current by 90 degree and VC lags the current by 90 degree, and VR is in phase with the current. Now Vs would be the total supply voltage, which would be somewhere between VL and VC depending upon the magnitudes of VL and VC. If VL is greater than VC, it would be in the upward direction, and if VC is greater than VL, Vs would be in the downward direction. Now we have assumed that VL is greater than VC, and we've plotted Vs as the total supply voltage as VL minus VC plus VR. This triangle that is formed, the right angle triangle, it is called the voltage triangle, and we can see that by Pythagoras theorem, Vs square is equal to VR square plus VL minus VC the whole square. So Vs is equal to root over VR square plus VL minus VC the whole square. Now VR is equal to IR, VL is equal to IXL, VC is equal to IXC. Therefore, taking I common, Vs comes out to be Vs is equal to I into root over R square plus XL minus XC the whole square. Now this whole term is substituted by a new term called as impedance or Z, and this is the impedance triangle that we see here. Your R is plotted as the reference, and XL and XC are plotted according to the phase differences, and Z is the total impedance. The angle phi is called the phase angle or the phase difference, and we know that Z is equal to R square plus omega L minus 1 upon omega C the whole square, the whole square rooted, and cos phi is R by Z. Now cos phi is also known as the power factor, and sin phi is equal to XL minus XC upon Z, and tan phi would be XL minus XC upon R. Now let us study series resonance. Why should we study resonance? Now, what would happen to the characteristics of the circuit if a supply voltage of fixed amplitude but of different frequencies was applied? And what would the circuit's frequency response behavior be upon the two reactive components due to this varying frequency? These are the questions that are answered by studying resonance. Now, in a series RLC circuit, there comes a frequency point where the inductive reactance of the inductor, that is XL, becomes equal in value to the capacitive reactance of the capacitor, that is XC. The point at which this occurs is called the resonant frequency, which can be denoted by FR or FO. And as we are analyzing a series RLC circuit, this resonance frequency produces a series resonance. Series resonance circuits are one of the most important circuits used in electrical and electronic circuits. They can be found in various forms such as AC mains filter, noise filter, and also in radio and television tuning circuits, producing a very selective tuning circuit for the receiving of the different frequency channels. Here is a summary of all the reactances that we have studied. Here we can see that XL is equal to 2 pi FL. So when we plot XL against frequency, it is a linear relationship as XL increases when F increases. It becomes infinity at an infinite frequency and is 0 at DC, that is 0 frequency. Now for capacitance or capacitive reactance, XC is equal to 1 upon 2 pi FC, which is an inversely proportional relationship. So as frequency tends to infinity, the capacitance becomes 0, and at a DC value, of supply voltage, the capacitance is approximately infinite. Now when XL is greater than XC, the circuit is inductive, and when XC is greater than XL, the circuit is said to be capacitive. And the total circuit reactance, as we've already seen, is XT is equal to XL minus XC, and the impedance can be given by Z is equal to root over R square plus XT the whole square. It can be written in the polar form as R plus JX. Now this is the series resonance frequency. This point is called the series resonance frequency. These are the two plots of XL and XC, as we have already seen before. And when the frequency is lesser than the resonant frequency, XC is greater than XL, so the circuit is capacitive, and when the resonant frequency is exceeded, the circuit becomes inductive, since XL becomes greater than XC. Now when XL is equal to XC, 2 pi FL is equal to 1 upon 2 pi FC. Therefore F comes out to be 1 upon 2 pi root over LC, or in hertz, or omega R comes out to be 1 upon root LC in radians. Now we can see that at resonance the equivalent circuit comes out to be a short circuit, since XL minus XC becomes 0, and at resonance the impedance of the series circuit is at its minimum value and equal only to the resistance R of the circuit, because both the other components become 0 cumulatively, and the circuit impedance at resonance is called the dynamic impedance of the circuit. The circuit current at resonant frequency will be at its maximum value of V by R, since the impedance is minimum, and this is the plot of current against frequency. We can see that at resonant frequency the current becomes maximum, since impedance is minimum. Now phase angle is the angle between the voltage and current of a series resonance circuit, and it is 0 at the resonant frequency point when Vi and Vr are all in phase with each other. The quality factor of the selectivity is given by omega RL by R, or XL by R, or XC by R, and it comes out to be 1 upon R to root over L by C. And the bandwidth is given by FR upon Q, that is the resonant frequency upon the quality factor, and it is between FH and FL, and the value comes out to be R upon L radians, or R upon 2 pi L hertz. That's it for this video, guys. Hope to see you again in the next one. Thank you.